Spoilers are a very common feature on airplanes, especially airliners. They're those flaps on the top of the wings that push up. For example, the next time you're on a plane, just look out the window at the top of the wing before takeoff, and when you see the pilots doing their checks, you'll see these plates just rotate up off the wing. Those are the spoilers. And pretty much every plane has them, but what are their exact effects on the wing's performance? How do they affect the pressure distribution over the wing, and how does that affect the subsequent lift, drag, and moment being produced over the wing? The wing's moment is actually very important because it dictates how stable and safe the wing is. What's more, how does the deflection angle of the spoiler affect the wing's aerodynamics? Is pointing it up better? And how much does changing the size of the spoiler affect the wing's aerodynamics? Is a smaller one really that much worse? And what happens if the wings aren't moving that fast? For example, airliners during takeoff and landing aren't traveling very fast. Are the spoilers still effective at these speeds? That is what we're looking at today in this podcast. We're looking at the effects of these spoilers on the wing aerodynamics. And this is really cool because these researchers looked at experiments. They did experimental results. And the reason why experimental results are so cool is because whenever it comes to planes, not many researchers have access to facilities that can accommodate the demanding geometric requirements. As such, it is becoming more and more common just to see CFD. In fact, it is so amazing just how much CFD has taken over the general field. For example, I remember back in 2016, I think, I was talking with the head of research at Northrop Grumman, and he said that they pretty much only use CFD. They literally do no wind tunnel testing. They literally just do their CFD. Then they were so confident with the CFD results that they then made planes and went out and tested them in real life. That is a big jump because that was back in 2016. They were already trusting their CFD that much already. And things have only become more CFD oriented since. So to have actual wind tunnel results in this field is a real treat. For these results, the paper we're looking at today is called Experimental Investigation of Spoiler Deployment on Wing Stall. So you can see this paper just up here once I scroll up. And it is quite a comprehensive paper, and the wind tunnel setup is pretty good. There are some things that they don't cover in as much detail as I would have liked, but they still go through things that are really good, like some really interesting points. So you can find this paper in the link below. It's open access. So let's get started. So in figure 1, they show the wing that they investigated. It is a very airliner-like airfoil. It is a NACA 2412, which means that it has a maximum camber of 2% of the chord that occurs at 40% of the chord. So about here from the leading edge. It also has a maximum thickness of about 12% of the chord, which is a middle-of-the-row thickness. Now, one thing that always surprises me is just how little camber you need to make the airfoil look very cambered. I mean, in figure 1 here, we have only 2% of the chord for camber, 2%. And it is very noticeably cambered, like you can see it from a mile away. And that obviously has a large effect on the lift. So anyway, there is also a spoiler located at 60% from the leading edge of the chord. And one really cool thing about the length of the spoiler is that they change it. So in this paper, they look at how different spoiler lengths affect the wing's performance. That's cool. And of course, like pretty much all spoilers, it can be deflected up at different angles. They tested the effects of different angles on the aerodynamics. So they tested this wing in a wind tunnel with a cross-sectional area of 1 meter by 1 meter, as you can see in figure 4. This is the setup down here. Now, here we get into some really cool stuff. So usually when you want to measure the lift and drag, you would use a load cell. And this is an instrument that you connect your object to, and then it registers the strain on the internal wires, and then through calibration curves, you can then find the forces on the object and hence the coefficients. These researchers didn't do that. In fact, they used a couple different and somewhat rare ways of finding these coefficients. The first way is to find the lift and the moment of the wing. They calculated them from the pressure measurements through pressure tappings on the surface of the airfoil. This is definitely a legitimate way of doing this, but it is so rarely done because it takes so much more time to set up, and it usually is a lot more expensive because you need to have high resolution and a lot of sensors then to place around your airfoil. And for those who don't know what pressure tappings are, well, there are two general approaches, I guess you could say. The first way is in the strictest sense of the word tap, which is where you literally drill holes into your object, then connect tubes to the holes, and then connect sensors to these tubes to then measure the pressures at each location. The second main way of doing pressure taps, I guess, aren't really pressure taps. I mean, because you're not drilling into the object, but it is effectively the same thing and is usually accepted as being a pressure tap. That is where you have a very thin piece of metal that has a hole in it on the surface where you want to measure the pressure. You then connect a tube to this piece of material, this metal with a hole in it, and then you place a sensor on the tube and measure the pressure. So in effect, it's the same thing. It's just that you use an additional component, the piece of metal, to act like a pseudo surface. You then measure the pressure from this surface, and so you don't have to drill into the object and permanently change it. Now, depending on which method you use, there are some things to keep in mind. So let's go through one that is common to both. That is the frequency response. So the frequency response is how quickly you can sample the flow. If you have a frequency response of 10 Hertz, that means you can sample the flow 10 times per second to measure the data. That is not always important. I mean, if you have a very steady flow, then you don't need to worry too much about the frequency response. I mean, yes, taking more samples reduces the random error because the random errors cancel out, but it's not that big a deal to have a frequency response of 10 Hertz or 500 Hertz. It makes no difference really for steady flows. If the flow is unsteady though, well, that is a different story. And now you want to have a frequency response at least twice that of the highest frequency you're expecting to see. That number of at least twice as high is because of something called the Nyquist theory. So I don't want to get too much into that because I've already opened a large can of worms with what we are talking about now. And if I go down this rabbit hole, then we can go on and on forever. So let me just say that the Nyquist theorem is, when it comes to a sinusoidal wave, you need to measure at least 2 points along that wave so that you don't mistake it for a different frequency. So that means you can just resolve this frequency accurately. So bringing this back to pressure tappings, if you have an unsteady flow and you have all different frequencies that flow physics occur at, for example, you might have a vortex being shed at one frequency, noise being produced at another frequency, and maybe some kind of vibration of the actual structure at another frequency. Well, it would be nice to resolve each of these frequencies so you can gain a better understanding of what is happening in the flow and why. To do that, you need to measure a high enough frequency. Well, when it comes to pressure tappings and the tubes attached to them, this greatly affects how quickly the flow you can sample. That is because when the holes of the tappings become smaller, the frequency response drops. You can't measure at higher frequencies anymore. Also, when the tubes have smaller diameters, the frequency you can sample at also drops. And the longer the tubes are, the lower the frequency you can sample becomes too. So in other words, to be able to sample at higher frequencies, you need to make the tapping holes have a larger diameter, make the tubes have a larger diameter too, and make the tubes shorter. The reason why making the tappings and tubings smaller and longer results in lower frequency responses is because doing these things now restricts the flow and doesn't allow the fluctuations in the pressure to move through the tubes to the sensors as quickly. So what does this mean when it comes to the two different pressure tapping methods that we just described? The one where you drill into the object compared to where you just have a superficial metal surface on top that you then have the hole in and then you have the tube coming out. Well, when you drill into the object, usually you can then make the holes have a larger diameter and locate the sensor closer to the holes because you have a lot of room inside the object to work with. You can hide all the tubings inside there and get very close to and the sensors as well, and then get very close to the holes. That means you can get better frequency responses if you usually drill into the object. Comparing that to the tappings where you have a thin piece of metal with holes in them stuck to the surface, because you want to make the metal as unintrusive as possible, you want to make them as thin as possible. That results in thinner tubing, and you don't want to place the sensors in the flow because that will just disturb the flow even more. I mean, imagine if you have your object and then you have all these sensors behind it disturbing the flow. So instead, you usually run the tubes out of the flow and then connect them to the sensors so that the sensors are no longer affecting your object. That means you have long tubes. So these tubes that are thinner and longer mean lower frequency responses. As a result, when you drill into the object to install pressure taps, you usually will get a better frequency response than if you use the thin pieces of metal. Anyway, that is pressure tappings, and these researchers used pressure tappings to find the lift and moment of the wing. But they didn't use the pressure tappings to find the drag coefficient. Instead, they used wake surveying, which we can see in figure 4, this contraption at the back here. They call it a wake rake, which is pretty cool. I've never thought of that term for it. I wish I had. It's a funny term, wake rake. Anyway, This is really cool because you rarely see wake surveying to calculate the drag coefficient. So wake surveying is exactly what it sounds like. You survey the wake. That means that you have a probe of some kind and you put it at different points in the flow. You measure the flow and then you know what the flow is doing at these points. One of the most common probes is a multi-hole pressure probe, which is a probe with several holes, as the name suggests. From this probe, you can then calculate the three orthogonal velocities. And from that, you can then calculate so many different things. You can calculate the velocity, you can calculate the induced drag, you can calculate the profile drag, just as some examples. These researchers from equation 5 seemed to be more just interested in the total and free stream pressures. Equation 5 is just up here, which is just really the total pressures to calculate the drag coefficient in total. So it's cool that they used wake surveying to find the overall drag coefficient. Now, they 3D printed their airfoil, and they don't say too much about treating the surface. And the reason why I bring that up is because 3D prints have a rough surface, and that can definitely change the flow physics. For example, if you were to align the airfoil so that the 3D printed layers are deposited from the leading edge to the trailing edge, you will then get striations running chordwise along the airfoil. These striations can actually mess with the boundary layer. For example, they can actually hinder the transition to turbulence because they hinder the three-dimensional breakdown of the turbulent structures. As such, the flow stays laminar longer. This is not necessarily a bad thing, but when it comes to research, it is just nice to know whether the surface was made smoother or just kept the same from the printer. So let's move on to a topic that I'm not too fond of, correction factors for wind tunnels. So as I mentioned, these researchers have touched on many interesting and important and even uncommon areas, and correction factors is kind of one of them. So they briefly say that they applied correction factors to the airfoil based on Barlow, Ray, and Pope's wind tunnel book, which is a great book. Now, the issue that I have here is that they don't say what the blockage ratio was. This is a big deal because if it was 10%, then even correction factors from Barlow, Ray, and Pope's book wouldn't be enough to give accurate results. On the other hand, if the blockage ratio was only 3%, then the results with correction factors applied would be very applicable. Now, me personally, I really don't like correction factors at all because it gives us a false sense of security about our experiments. So, for example, if you have a big object in your wind tunnel, then that will alter the flow around it and change the flow physics and hence the forces. No general correction factors can account for that. You can't account for the change in flow physics. If you do wake surveying and then put correction factors on that, it won't really work properly. We'll get different streamlines, etc. And applying them will just make us feel better about trusting our results when we really shouldn't. So for me, in a closed test section, a blockage ratio below 3% is fine. Above that, you start to have to apply significant corrections, and above 5%, I don't really see the point of even running the test. The flow physics will be too different. So from my calculations at the maximum angle of attack tested here, which is 30 degrees, the blockage ratio of this airfoil was 15.4%, which is really high. I wouldn't trust the results when the blockage ratio is that high in a closed wind tunnel. From what I can tell, a 3% blockage ratio was hit at an angle of attack of 6 degrees, and a 5% blockage ratio was hit at about 9.3 degrees. So for me, below 6 degrees is completely good. Above 10 degrees, we shouldn't really trust too much. Let's get into the results now though. In figure 5, we have the lift coefficient plot from -7 degrees to about 33 degrees, and for different deflection angles of the spoiler and different lengths of the spoiler. So first, there is a very clear trend of the more the spoiler is deflected up, the more the lift curve is pushed to the right of the plot, as we can see here from the red to the black. What this means is that the wing still produces the same amount of lift, but it does so at just a higher angle of attack. So for example, with no spoiler, which is this red line here, at 10 degrees, which is this point here, the wing produces a lift coefficient of about 1.05. And now if we were to put a spoiler deflected at 8 degrees, the blue line, the wing still manages to hit a lift coefficient of 1.05, but that now occurs at an angle of attack of about 12 degrees, which is this one here. So the spoiler itself doesn't seem to affect the overall lift produced very much, but it mainly just delays the angle of attack at which it does occur. And yes, you could argue from this plot that perhaps the spoiler does reduce the lift coefficient a little bit as we go along, but I don't know what the error bars are for this plot, so I can't really conclude that. Whereas the trend of simply pushing the lift curve slope towards the right is definitely occurring here. It's like even if they have big aero bars, we can still see that it is really occurring. Now, that is for the deflection angle of the spoiler. We know that a greater deflection angle pushes this curve more to the right. What about how big it is, the spoiler itself? We can find out that by comparing the blue line, for example, to the green line, or the yellow line, which is just here as well, to the cyan line, or the pink line to the black line. They're the two coupled ones, just showing different lengths of the spoiler. So the trend isn't that clear, but I would say, if anything, a larger spoiler exacerbates the shift of the lift curve slope more to the right. So if you want to get to a certain lift coefficient, you have to go to an even greater angle of attack now with a longer spoiler. And that makes sense because if you have a spoiler in general, it is delaying the lift coefficient, then a bigger spoiler would probably do that even more so. So one really weird trend I'm seeing on this plot is that the stall pattern of the wing with the spoiler deflected isn't really like a regular wing stall pattern. I mean, we see with a clean configuration, which is the red line here, when it stalls, it just drops down. It occurs as we would expect. From there, the lift coefficient stays low. That is not the case with some of the spoiler configurations. Namely, when the spoiler is larger, the cyan and black lines here, for this spoiler configuration, the wing stalls, but then when the angle of attack increases again, the wing unstalls, like it's now producing the same lift as it was pre-stall. So there was a stall angle attack and now it's gone back up. So there's this dancing around going on. Now, I don't know why this happens, and there isn't any flow viz later in this paper to help us figure out why that is happening. I guess this is just supposed to be one of those mysteries of life. Anyway, that is the lift coefficient. Now let's look at the drag coefficient in figure 6. So the drag coefficient is very affected by the spoiler, way more than the lift even. So without the spoiler, so in the clean configuration, which is the red line here, the airfoil has a typical drag bucket where the drag coefficient is low and then skyrockets once stall sets in, up around here. At its lowest point, the clean airfoil is producing a drag coefficient of 0.009, which is really low. When you introduce the spoiler, regardless of the deflection angle and the length of the spoiler, the drag coefficient is now much high. You can see how much it's just jumped up. That makes sense because you now have this plate just sticking up into the flow, and that is obviously going to create a larger wake. And that is going to be a higher drag coefficient. And we can see that in figure 11, where we have the normalized velocity downstream of one of the wings. Let me scroll down to it first. Figure 11 is down here. So we have the normalized velocity downstream of one of the wings with the spoiler and in the clean case. So the clean case is the red line, the spoiler case is the blue line. So for the clean case, the wake deficit is definitely there. We can see that there is a lower velocity just behind the wing, but when you have the spoiler on, which is the blue line, the wake deficit is now much greater. It takes up like twice the distance, so this whole region here is much greater. And that tells us that the wake is larger, and hence where this additional drag is coming from. So coming back to the drag coefficient in plot 6, here we go. So coming back to this drag coefficient here, it is clear as day that the more the spoiler is deflected up, the greater the drag becomes. So going from the blue line, which is the spoiler at 8 degrees, all the way up to the pink line, which is 25 degrees, we can see a great increase there. I mean, remember in the clean case where the lowest drag coefficient was just 0.009? Well, for the worst spoiler, which is the black line here, the lowest drag coefficient is like 0.064, so like 7 times as much as the clean case. A 600% increase just by putting on a spoiler. And okay, this spoiler has a length of 15% of the chord and deflected at 25 degrees, but still this drag coefficient is really huge for any wing. Another trend that can be seen here is that the larger the spoiler is, the greater the drag coefficient becomes. That again makes sense because the larger the spoiler is, the greater this flat plate is just sticking up into the air. And that is going to create a larger wake with more drag. So the effects of the spoiler on the drag coefficient aren't that surprising when you think about it. But what I'm always surprised at when it comes to wings is how some flow control devices can greatly affect the drag coefficient while leaving the lift coefficient relatively unaffected. I mean, take this spoiler for example. The effect it has on the wings are very large. I mean, we saw a 600% increase in the drag coefficient, But in figure 5, the effects on the lift coefficient are relatively small in comparison. So for this particular airfoil with this particular spoiler, the drag coefficient is definitely the thing that gets affected the most here. And it kind of makes you wonder how the drag coefficient can be affected so much, but the lift coefficient not really affected that much by comparison. Well, we don't have that much information here about it, but figure 9 gives us some idea. So let's scroll down to figure 9 here. Here we go. So figure 9 shows the pressure coefficient plot over the clean airfoil and the airfoil with the shortest spoiler, deflected at the least amount, only 8 degrees. And if you don't know what this pressure coefficient plot is and how to read it, check out the video on our YouTube channel called Airfoil Pressure Coefficient Distribution, Aero Fundamentals number 46. In that video, we go through what this is and explain what the graph is and how to read it. So we know that the wing with the spoiler doesn't produce less lift, just you have to pitch the wing to a high angle attack to get the same lift coefficient. That maximum lift coefficient are pretty much unaffected. So in figure 9, we see the wing at a 3.7 degree angle attack. The clean airfoil has a very expected pressure coefficient plot with the upper and lower surfaces quite far apart from each other, so these red lines here. And the wing with the spoiler has a very unusual plot for a wing. In fact, the area between them is much less, and this plot shows that most of the lift is being produced in the back half of the wing down here, so the distance between these two lines. And that's in fact actually behind the spoiler. So it seems like the spoiler is creating a low pressure zone behind it, and that goes a long way to produce the lift. And while this pressure coefficient plot looks strange, I guess if we think about it, it does make sense. So for example, for a regular wing, the only reason why we get the low pressure on top is because the flow accelerates and hence the pressure drops. Well, if you have a spoiler sticking up, that is going to block the flow a little and stop it from accelerating so much. As a result, the pressure coefficient won't be as low because it won't accelerate as much. That is what is going on here in the front half of this wing. Now, the fact that the lift we lose on the front half of the airfoil is made up on the back half is quite strange to me. Maybe there is some kind of continuity law going on here or something. I just find it strange that the loss is just somehow made up with the gain in another location. It's kind of like when you forget like your lunch at home and then you go to work and there happens to be a free lunch at work for everyone. The bad and the good somehow magically cancel out. Also, it is worth noting that the pressure coefficient on the underside of the airfoil with the spoiler also reduces in pressure more than without the spoiler. So we can see it's lower here, a more negative value. To me, I really think that the spoiler is restricting the airflow over the top of the airfoil, so that more air has to go underneath the airfoil, and that leads to acceleration, hence the pressure drop we see here. That's why we're getting this pressure drop on the undersurface as well. So after all of that explanation of the pressure coefficient plot, we get a better understanding as to why the lift coefficient doesn't seem to be affected that much compared to the drag coefficient. It's because the lift reduction in one area is made up for in another area. And because we have a low pressure zone directly behind the spoiler, and not to mention the high pressure zone in front of the spoiler here, that increases the drag on the spoiler and hence the overall wing. It's pressure drag that's forming here. That is the lift and drag, but there is also more to a wing's performance than just those two parameters. Let's move on to one which measures the wing's efficiency, the lift to drag ratio. So in figure 7, let's scroll up to that one here. We see the drag polar plots, which are in effect the lift to drag ratios. So if you don't know how to read these plots, I'll quickly go through the salient points. So the first one is the drag coefficient is on the x-axis and the lift coefficient is on the y-axis. The next important point is that if you want to find the maximum lift to drag ratio of each wing, what you have to do is draw a line from the origin, so just here, to the each wing's line, such that the slope is the greatest possible. So if we were to do this for the clean wing, the red line here, which I would then try to find the greatest slope from the origin and then shoot all the way up to about here. That would be the greatest slope, this third point here. And that would give us a lift to drag ratio of about 0.55 on 0.01, which gives us about 55. That is pretty decent for a wing. As expected, because the spoilers negatively affect the drag coefficient and push a lift coefficient to the right of the plot, the spoiler in any configuration reduces the maximum lift to drag ratio. And because the negative effect of raising the spoiler into the air, that also greatly reduces the drag ratio even more in general. So the greater you lift the spoiler up and the bigger the spoiler is, the worse the lift to drag ratio becomes. That's understandable. We have a greater drag coefficient and not really changing lift coefficient at all. So we can kind of conclude here that the spoilers are bad for the efficiency of the wing. So the next parameter of these wings, these authors include, was the moment coefficient. And this is how much the wing itself wants to pitch around. And generally you want a negative pitching moment and for it to be as flat as possible. This is in figure 8 here. At the very least, as predictable as possible, you want this line. So the flatter this line is, the more stable and predictable this wing will be. The more it goes up and down and it's discontinuous and you just get these jumps, then that makes the plane, the wing, and probably the plane it's attached to, very hard to predict and hence very erratic and probably unsafe, dangerous. So that's because, like, let's say you're at 5 degrees and you're going along steadily and you go to 6 degrees and all of a sudden the plane wants to pitch down a lot, that the pilot then has to react to that and recover. So that makes and even worse if you had to pitch up, that's even worse because then that leads to stall and that makes the airplane even more dangerous. So ideally you want this line to be as predictable as possible and ideally flat. So on that score, we can say that the spoilers mostly make the pitching moment coefficient worse in that they are generally less negative, as we can see here. And once you start to get around stall, the pitching moment coefficient drops dramatically, which is to be expected, but still it makes it hard for the pilot to recover the plane and restore level flight. That is dangerous. So with that, we come to the end of this podcast. There were a few surprising effects of spoilers on wing aerodynamics. For me, the fact that the changes in lift cancel out were interesting. I liked the pressure coefficient plots as well because they gave us a lot of information about why wings were behaving the way they were with spoilers. So if you like this podcast, hit the like button and the subscribe or follow button, whichever platform you're on. And if you want to learn how to do OpenFoam, which is a really good and free CFD software, but really difficult to learn, then take our course and link below. We go through it step by step and literally from even how to install it. We also have other CFD courses to help you improve your skills, so you can find them in the links below. And if you do experiments, then did you know that you probably have a 2 to 4% error in your data that you collected and you don't even know it? So to correct that error, we made the Atmosphere Hawk. And you can find that in the link below, along with the math showing how a 2 to 4% error easily occurs in most wind tunnel experiments and how to correct that. So that is the end of this podcast. I'll see you next one. Peace, amigos.